Next slide. Now we skip forward about 1400 years. After the devastation of the bubonic plague that killed off a third of the European population and several bloody wars, things settled down politically for people to move beyond just trying to survive. The time period in European history called the Renaissance brought a rebirth of discovery and desire for exploration and explanation. Through the centuries, Ptolemy's model had been modified to fit the current observations, and it had become very complicated with many epicycles on top of larger epicycles and other adjustments. That complexity struck some people as a sign that something was wrong with it. Scientists use a guiding principle called Occam's razor to choose between two or more models that accurately explain the observations. This principle, named after the English philosopher William of Ockham, who stated this principle in the mid-1300s. It says, "The best model is the simplest one, the one requiring the fewest assumptions and modifications in order to fit the observations. Nature prefers the simplest, most elegant solution." It was for philosophical reasons and theological reasons that a Polish clergyman named Nicolas Copernicus proposed a heliocentric model, one that puts the sun at the center of the universe. He still retained the idea of planets moving with uniform speed in circular orbits. The planets farther from the sun moved slower. Earth became a planet, the third planet from the sun. His model easily explained retrograde motion as an optical illusion that happens as we pass by the planet. That also explains why the planet appears brighter when they're undergoing retrograde motion. When you select the image, you'll bring up an animation of the retrograde motion. As the Earth passes by a planet, the planet appears to move backward against the background stars. Retrograde motion is an optical illusion, just as a slow-moving bus appears to move backward with respect to you in your speeding car as you pass it up. Copernicus's model still had circle motions, and it was just as accurate as, that is, no more accurate than, Ptolemy's model in predicting planet positions among the stars. Although it was no more accurate than Ptolemy's model, Copernicus's model was a simpler calculator to use, so that was a plus. Many people would use Copernicus's model, but not believe it was reality, because the Earth does not feel like it is moving. Even more damning was that no parallax was seen in stars, as you should see if we were in fact moving around the sun. In the parallax effect, the farther away a star is, the smaller is the parallax. Scientists did look very hard for the parallax and couldn't find it. So, using the best evidence at hand, they made the reasonable conclusion that we cannot be moving around the sun. We now know that the stars are incredibly far away, and that it requires a telescope to see the parallax of even the nearest stars. It wasn't until the late 1830s that telescopes were powerful enough to see the parallax. The nearest star outside the solar system has a parallax smaller than 1 second of arc, or the thickness of a credit card is seen from across the length of a football field. You definitely need a telescope to see parallaxes that small. The next person in our quick tour of astronomy history is Galileo Galilei, who is also sometimes called the father of modern science. Although Galileo did not invent the telescope, he is the first one we know of to use a telescope for astronomy. A telescope is like a big eye on the cosmos. With his superior eye, he discovered many things. 1. Instead of just a few thousand stars you can see on a dark sky, he was able to see many tens of thousands. If the fainter stars are farther away, then the universe he could see became much larger than before. 2. The moon has mountains and craters, and there are spots on the sun. This meant there are other rough places with change and decay like the Earth. There were other worlds to explore. 3. There are 4 large moons orbiting Jupiter: Io, Europa, Ganymede, and Callisto, also known as the Galilean satellites in his honor. In this system, Galileo saw a mini model of the heliocentric system. The moons are not moving around the Earth, but are centered on Jupiter. Perhaps other objects, including the planets, do not move around the Earth. Number 4. Venus goes through a complete set of phases, which is only possible if Venus orbits around the Sun. Ptolemy's model was still the leading geocentric model in Galileo's time. In that model, Venus was always situated in between us and the Sun, so Venus should have only been seen in a crescent or new phase. The only way to arrange Venus to make a gibbous or full phase is to have it orbiting the Sun so that, with respect to our viewpoint, Venus could get on the other side of or behind the Sun, farther away from us than the Sun. This was possible only if Venus orbited the Sun. Being able to disprove Ptolemy's geocentric model was enough to prove to Galileo that Copernicus was correct. Galileo is often considered the father of modern science because his ideas were not derived from thought and reason alone. He used the guidance of nature, experiments, to figure out how things move under different circumstances. This marked a revolutionary change in science. Observational experience became the key method for discovering nature's rules. With his experiments, he found that long-held ideas of Aristotle's physics were wrong. We'll touch on some of those in the gravity lecture.